Okay, third lecture for complex manifolds. So what did we do last time? We defined what a complex manifold is by just taking the definition of a smooth manifold and replacing the word smooth by holomorphic. So that means we've got a topological space together with a bunch of charts, i.e. a covering by open sets, homeomorphisms from those open sets into open subsets of complex, m-dimensional complex space now, not Rm, but Cm, in such a way that on the overlaps, you get these transition functions, and these transition functions we want to be holomorphic maps from Cm to Cm, right? Not just smooth maps from Rm to Rm, but now holomorphic maps from Cm to Cm, meaning that when you fix all the coordinates except one, then you have a holomorphic map of a single variable. Okay, and then we defined a m-dimensional complex manifold to be a topological space equipped with an equivalence class of an m-dimensional holomorphic atlas. Okay, and a map between complex manifolds is called holomorphic if at the level of charts, once you get a map between Cm and Cn, then this composite map here, which is just a map from an open subset of Cm to an open subset of Cn, that map has to be holomorphic. Okay, again, meaning when you fix all the coordinates except one, then that's a holomorphic function of a single variable. Okay, so then I ended with this example of the two-sphere, which is my favorite complex manifold. So thinking of the two-sphere as just the set of points in R3, which has normal 1, and I can put two charts in it using stereographic projection. I can stereographically project from the North Pole. That would then give me a projection between everything away from the North Pole and the complex numbers. And this is the formula for stereographic projection from the North Pole, but we have to adjust the formula a little bit. If you were to stereographically project from the North Pole, you'd have a plus there, and we needed to make it into a minus. As you'll see in a second, the reason is if we combine stereographic projection from the North Pole and from the South Pole together to get our charts into the complex numbers, then that would then, at the transition function, would map Z to 1 over Z bar. And that was an exercise. So that's why we needed to put a minus here. So it's not exactly stereographic projection from the North Pole, it's complex conjugate of stereographic projection from the North Pole. Then at the level of the transition functions, Z will go to 1 over Z. So that's holomorphic function. So that's a holomorphic atlas on the two-sphere. Okay. There's another way of thinking about the two-sphere. You can think about it as one-dimensional complex projective space. Okay, what is one-dimensional complex projective space? So as a set, it's a set of one-dimensional subspaces of C2 as a complex vector space. So a one-dimensional subspace of C2, it'll be, if you think about it, it'll be a, let's call it a line. Obviously it's not actually a line graphically because it's got two real dimensions, but it's got one complex dimension. So we'll just call it a line. So a line in C2, i.e. a one-dimensional subspace of C2, is a point in CP1. But CP1 is the collection of lines in C2. And we can topologize that, in other words, put a topology on it by understanding that the set of lines in C2 are specified by giving a point in C2. But that's too much information because if you scale that point by a number, you'll deliver the same line, right? So the point on the line specifies that line, but a similar point that's been scaled by non-zero complex number specifies the same line. So if I want to talk about just about the lines, then I have to talk about pairs of points. Subtract away the origin there because the origin is not going to give us a line. And then up to scalar multiplication by a non-zero complex number. Okay, and so we've got this equivalence relation here and an equivalence class in in that equivalence relation is written with square brackets and a little colon there. So we call that homogeneous coordinates on CP1. All right. So how do I think of this as a complex manifold? Well, I've got two charts. The one chart is where this first coordinate here in the homogeneous coordinate is non-zero, because if this first coordinate is non-zero, then I have a bijection between such points and the complex numbers. Why? Giving me such a point like this, where the first coordinate is non-zero, I can map it to the second coordinate divided by the first coordinate. All right. Why is that well defined? Well, I've got to check that this is well defined. In other words, if I were to simultaneously scale Z0 and Z1 by lambda, then the output here should remain the same. And that is indeed the case, because they'll have a lambda on the top and on the bottom. And the inverse map is just going to send Z to 1Z, right? So that gives us a bijection between this chart and the complex numbers. Similarly, there's a bijection between the other chart and the complex numbers, where the other chart is where the second coordinate is non-zero, because then I can divide through by the second coordinate. All right, so let's calculate those transition functions. Well, if I were to start with a point over here, and then I'd map it using the inverse of the first chart, says that that point will go to 1 colon Z. And what does the second chart do? Second chart takes a point and then sends it to a complex number, which is the second, the first coordinate divided by the second coordinate. So I take this divided by that. So I get 1 over Z. So the map sends Z to 1 over Z, which is indeed a holomorphic map. So this is a holomorphic atlas. And in fact, we've got a holomorphic diffeomorphism between the two sphere as a complex manifold and the CP1 as a complex manifold, which is just the composite as follows. So the two sphere, using stereographic projection from the south pole, it's going to be in bijection with the complex numbers union a single point, the point at infinity, which would be where the south pole gets mapped to under stereographic projection. And this set is in bijection with this set under this map here. So that's actually going to be a holomorphic diffeomorphism between S2 and CP1. Of course, there's an exercise to check this. So you have to check that. What have I written down here? I've written down I've written down a map between two sets, this set and that set. And now you have to check whether that map is actually a holomorphic, and it's clearly a bijection. You have to check whether it's holomorphic, right? So you have to check that in the charts. Okay, so more generally, we've got n-dimensional complex projector space, which is going to be the set of one-dimensional subspaces of Cn plus 1. So a point in CPn is a one-dimensional subspace of Cn plus 1. And you can equip with a holomorphic atlas in a similar way. You can think of it as Cn plus 1 modulo and equivalence relation. You can talk about these homogeneous coordinates, and you can get charts where each of the coordinates is non-zero. And yeah, this gives us a nice compact complex manifold, right? All these CPNs are compact complex manifolds. Think about CP1, it's compact. How do I know it's compact? Well, the easiest way to see it is that it's holomorphically diffeomorphic to the two sphere, which is a compact manifold. All right, so that's CPN's our first example of a n-dimensional complex manifold. Of course, there's always Cn, but now this is our second example. All right. By the way, a Riemann surface is by definition a one-dimensional complex manifold. And the magic of Riemann surfaces is that they can be written down in various ways and using different constructions. And then it's just sort of a miracle that you can compute something in the one formalism, and then you can compare it to how you would compute it in the other formalism, and sort of you get these amazing equations. Okay, so I've given you two examples so far of complex manifolds, the two sphere and CP1. Okay, and I've also given you CPN. Let's give another example. just at a more basic level, every open set in the complex plane is going to be a complex manifold, right? For example, complex numbers themselves, or the unit disk. By unit disk, I mean the open unit disk, where all the length of the complex number is less than 1. So recall the Riemann mapping theorem, which says that every connected open subset in the complex plane, which is not the entire complex plane, is holomorphically in bijective correspondence with the open disk. Right, so this is very nice theorem from the 19th century. Take any open set in the complex plane, which is not the entire complex plane, then it's going to be holomorphically diffeomorphic to the unit disk. And there's a specific map that you can write down. So that's very cool. So that tells us that that all of these open sets in the complex plane are not giving us different complex manifolds, because they're all isomorphic to each other, because they're all isomorphic to the unit disk. Okay. However, the unit disk itself is not isomorphic as a complex manifold to the complex numbers. Why? Well, it takes a little bit of work, but one way to check that these are not the same is because you can compute their automorphisms. In other words, holomorphic bijections from these spaces to themselves. And you compute that for the unit disk, and you'll find it's the collection of maps of this form, where the norm of a squared minus the norm of b squared is 1. So there's 3 parameters, or there's 2 complex parameters here, a and b, and there's a single equation. So that's a 3-dimensional real Lie group. Okay, there's 3 free parameters here. Whereas the holomorphic automorphisms of the complex plane, thought of as a complex manifold, it's actually just a collection of maps like this. It's just scaling and translation, right? There's the scaling, there's the translation. And of course, the scaling parameter has to be non-zero, but you've still got two real dimensions there. And the translation parameter is a non-zero complex number. So there's 2 parameters there. So at the end of the day, there's got 4 free parameters in the symmetries of the complex plane, but only 3 in the symmetries of the disk. And so that's the sort of most brutal way to see that these 2 complex manifolds are not isomorphic. They are isomorphic, they are diffeomorphic, right? Because I can take the disk and I can just scale it up, and I can the unit disk is diffeomorphic to the complex plane, right? Because I can, for example, just scale it up by the arctan or something that would have the effect of taking this radius and scaling it to infinity. So the unit disk is diffeomorphic to the complex numbers, but it's not holomorphically diffeomorphic. And that's very interesting. Okay, here's my favorite example of a Riemann surface. So suppose you have a topological surface that you obtain by gluing together the edges of a collection of Euclidean triangles together in pairs. So in other words, a triangulation of a surface. So in other words, you start with a bunch of triangles like this, Euclidean triangles, so you can think of them as sitting on your table. And then I identify edges pairwise. So this edge gets identified with that edge, and this edge with that edge, say. So you got some scheme for identifying these edges pairwise together. So you're going to glue all the edges together, and that then gives you a surface, right? This quotient space is a surface, the disjoint union of these triangles modulo this equivalence relation. This particular surface I can actually visualize in R3 because I can put these triangles together to form this shape here. But in general, if you glue a bunch of triangles together, you're not going to be able to, it'll just be some abstract surface, right? But nevertheless, this abstract triangulated surface is going to have a very nice structure, holomorphic atlas on it. So one other simple example here, I can just take 2 triangles and I can glue them up like this. So this edge gets glued with that edge, this edge gets glued with that edge. That's going to give you, and then this with that, that's going to give you a sort of a donut shape, right? But I put inverted commas here because when you, it's not that round donut. It's the abstract space formed by gluing these these Euclidean triangles together. Okay. So, given any triangulated space that you form by gluing triangles together, you can place a very nice holomorphic atlas on that surface as follows. Okay, so I have to give you a system of charts. It seems weird, right? I've sort of got gluing things together, and how am I going to make this into a complex manifold? Well, let X be a point on the surface. So I've got three possibilities. The first possibility is that X is not a vertex or an edge. So it's just an interior point for one of the triangles. Then I can choose a disk, U, around X that lives entirely inside the triangle. And I can just sort of use the identity chart, right? So I've got this open set U, and I just, that disk is itself the chart. Okay, happy? The second possibility is that X lies on an edge, but not on a vertex. Then that means there's going to be two triangles that are incident with that point. And the chart is the disk obtained as the two half disks joined together. So if this is your point X, then you're going to get a chart like this. You know there's another edge which is glued to that point. So I draw a half circle there, and then I've got these two disks. And then my chart is just going to then map that to the glued together disk. All right. If you want to see the picture here, X would be living sort of along this line here, right? And there's X there. All right, so in the final possibility is that X is going to be a vertex. So what do we do then? Well, we consider the disk U that's made up of the sectors composed out of all the triangles incident at X. And they're going to span an angle alpha, which might not equal 2 pi. It might be less than 2 pi if you've got positive curvature, and it might be more than 2 pi if you've got negative curvature. And then you can simply find a map which is going to sort of squash the angles or increase the angles so that the circle does have 2 pi in total angle. And that'll be this map here, if I want to write it down as a complex map. And that's going to map U one-to-one onto a disk in the complex numbers. So think of it like this. Suppose I'm gluing these triangles together. So maybe this is glued to that, this is glued to that, and this is glued to that. Then that would sort of form a sort of a vertex in R3 if I want to visualize an R3 and sort of got positive curvature. So the point is, here is this U, this open neighborhood of X, and you can see that as I run around this circle, I don't quite go through 2 pi. I go through something less than 2 pi. So I just map Z goes to Z to the 2 pi over alpha. And that's going to stretch out this disk into a full disk. Okay, so this little pink section got stretched out into that pink section there. And that gives me a chart near X. And then, yeah, exercise. Check that this is a holomorphic atlas for the triangulated space. Very nice construction. Okay. Here's another very general construction of a Riemann surface. So algebraic curves. So suppose you're given a polynomial, P of two variables. Then I set X to be the set of points in C2 where the polynomial vanishes. Now this is going to be a Riemann surface under certain conditions. So the condition is, so suppose that for all points in X, the gradient of the polynomial, and by the gradient of this polynomial, I mean the partial derivative in the Z direction, comma, the partial derivative in the W direction, is not the zero vector. In other words, one of these is non-zero. Okay. We had this condition before, if you remember the in the implicit function theorem, which was way back here. Yeah, right. The implicit function theorem said that if you've got a map like this, and when the when the derivative is surjective, then so this is a more general statement, but if I can apply it to the case where m equals 1, then that derivative will then just be working out the gradient. Okay, and then it tells us something very nice about how the level sets of H are sitting. And now we're sort of doing a holomorphic version of the same theorem, which is true. So I've got a polynomial, and I'm looking at the zero set of the polynomial. And I'm supposing that at all points on that zero set, the derivatives of the polynomial in the two directions don't simultaneously vanish. So what does this mean? Like, if the derivative of p in the w direction is not naught at a given point, then that means that near that point, we can express w as a function of z. Okay, and not only w as a function of z, w can be expressed as a function of z in a holomorphic way. And that's by the holomorphic version of that implicit function theorem that I stated earlier. All right, so that means we can parameterize the points of x. So if the partial derivative of p with respect to w is non-zero, then we can parameterize the points in x near that point as follows, right? I can use a single coordinate z to parameterize them, and z would get mapped to the pair z comma w of z, because this condition is telling me that w can be written as a function of z. Okay, and similarly, if the gradient or the derivative of p in the w direction is not zero, then you can express z as a function of w. Okay, so then I'd have this parameterization of x available to me. And most times you have both parameterizations available to you, right? But at certain points, you might only have one. So in this way, we get a holomorphic atlas for x, and that's actually an exercise, right? We call x a smooth algebraic curve. So let me write this down as an exercise. Okay, so you have to compute the transition functions here. So this is called a smooth algebraic curve. It's algebraic because it's given as a zero set of a polynomial, not the zero set of some transcendental function. All right. So let's have an example here. So, for example, consider this polynomial, w minus z squared. So what is x? It's the collection of points z comma w, where w minus z squared equals 0. And the claim is that this, you can put, this is a complex manifold, you can put a holomorphic atlas on it. So to visualize this, just x is living inside C2, but let's just visualize it inside R2. Okay, so I've got the z-axis and the w-axis. So what the zero set of this polynomial will be where w equals z squared. So that's this parabola here, right? That's x. You can see it's a nice smooth space. Now, where the derivative of p with respect to w is non-zero, what is the derivative of p with respect to w? It's just 1. So it's actually non-zero everywhere. That means I can write w as a function of z. And that's clear because you can see this red line here is, you can write w as a function of z everywhere because w is actually equal to z squared, right? But at certain places, I can also write z as a function of w. That will be when the derivative of p in the z direction is non-zero. Derivative of p in the z direction is minus 2z. So it's non-zero everywhere except at the origin. So I can't do that at the origin. But away from the origin, like for example over here, if I'm in the neighborhood of this point, then I can write z as a function of w, right? And near this point. So in other words, I can use w then to parameterize this neighborhood in x, right? You see, here's the chart that's going to be mapping this neighborhood to this w coordinate. I could also map this neighborhood to its z coordinate. That would be a different chart. All right. So these are the charts for X. Okay, I hope that's clear. So more generally in higher dimensions, a space of this form, so a set of points in Cn where a bunch of polynomials vanish, and the smoothness condition here, instead of saying that the gradient is non-zero, you talk about the rank of the Jacobian. In other words, the derivative is surjective. That's that implicit function theorem. If that derivative is, or I should rather say has maximal rank, then this guy is going to be a smooth complex manifold. I mean, and now it's called a smooth algebraic variety because it's algebraic because where it's a bunch of polynomials are vanishing, right? Okay, so the way to understand this Riemann surface thing here, by the way, just an important philosophical point, is what is it really telling us? It's a certain surface but it's not just any old thing. It comes with the projection maps onto each coordinate, right? You see, I can take a point ZW on X, and I can actually map it to, for example, W or to Z. But let's think about the map to W for now, because that's the more non-trivial one. Because this allows us to think of X as a rigorous holomorphic mental construct which expresses Z as a multi-valued function of W. See, we all happy where this polynomial vanishes. For this particular polynomial, it's very clear to see that, right, what does it mean? It means that W equals Z squared. So clearly W is a holomorphic function of Z because W equals Z squared. But dually, I can also think of Z as a holomorphic function of W, but then I have to think of it as a multi-valued function because there's two roots, right? And it's slightly more complicated than that because at a certain point, the two roots become one root exactly at the origin. So how do I make that rigorous, this idea that I have this multi-valued function where it's that is some places got 2 points in it, some places got 1 point. Very difficult to write that down in a rigorous way, but this Riemann surface is allowing us to do that, right? It constructs this smooth space X with this really a complex manifold, and then the idea is now this function which I was trying to make rigorous, this multi-valued function which maps W to power inverse of W. In other words, it's the function which is trying to make sense of the notion of taking the square roots of W, the multi-valued function given by the square roots of W, because there's actually 2 square roots for every point except the origin, and there's only 1 square root. But now we're able to make rigorous sense of this in a very clear and geometric way. So that's the raison d'etre for Riemann surfaces. Okay. So the Riemann surface is more than just a complex manifold. The Riemann surface of a smooth algebraic variety is more than just a complex manifold. It comes equipped with this extra data, but at the very least, it is at least a complex manifold. Okay, so just to be clear here, I'm thinking of the function which assigns to a point W the inverse images of that under pi. So that would be this point and this point. So it is like a function of W, but it's a multi-valued function of W. So at each point here, it assigns this 2-element set. And then in fact, as W goes down to 0, eventually there's just going to be a single element in that fiber. They all come together nicely to form a smooth space. That's the magic of Riemann surfaces. Okay, so one thing I want to point out here is that this X that I've defined, which is the vanishing set of the polynomial, that's not actually going to be compact, as you can even see in this picture, because the parabola goes off to infinity, so it's not compact. So there is a compact version, which you often want to deal with. The compact version you write as X bar, and so the non-compact version is living inside C2. The compact version is going to be living inside CP2, complex projective space. And how do you obtain the compact version? Well, what you do is you start off with your original polynomial, small p, which is a function of two variables, and you homogenize it to get a homogeneous polynomial which has three variables in it. So I add this sort of dummy parameter t, and I add powers of t to homogenize the polynomial. So in other words, if this was my original polynomial, z to the 5 minus 2z squared w minus z cubed w squared plus w. See all sorts of different powers appearing. Then I could homogenize that by adding a dummy variable t, and I just add powers of t to make sure that this new polynomial has got the same degree, which I can take to be 5, because that's the highest power that I had. So this guy didn't have degree 5, so I multiply him by a t squared. And similarly, this guy did have degree 5, is okay, but this guy didn't, so I multiply him by t to the 4. Okay, so there's this unique way you can homogenize your original polynomial. And what's nice is that now I can think about the zeros of this polynomial inside CP2. Right? So I set x bar to be the set of points inside CP2 where this polynomial vanishes. A little subtlety there. This polynomial can't be thought of as a function on CP2 because if I were to scale all these three coordinates, then I would get out a different number out here, right? It's not a function, so it doesn't make sense to say what's the value of p at a certain point, but it does make sense to say is p 0 or non-zero at a certain point. So this equation here does at least make sense. Okay. And that's actually going to give us a compact Riemann surface. Why? So why is it a compact Riemann surface? Because it's going to be a closed subset of a compact space. CP2 is compact. This subset is closed because it's the set of points where something equals 0, right? Where a continuous function equals 0, so it's the inverse image of a closed set. If you like, yeah. So again, there is a smoothness condition here. I need that this capital P, its derivatives mustn't all be 0. But providing that's the case, then I get this nice compact version of x. We call that a smooth projective algebraic curve. And it's very useful theoretically. Okay, so you should notice that the compact version of x can be thought of as the original affine version of x, together with a finite number of points at infinity. And those new points are going to be exactly the points where this first dummy coordinate was 0. Okay, because when that dummy coordinate is 0, if the dummy coordinate is non-zero, then you might as well take it to be 1, and then you can set that t equal to 1. And if I were to set t equal to 1, yeah, then I'd just be getting the zeros of my original polynomial. But when this dummy coordinate is 0, then I'm getting some, in principle, new points out. So for example, if I were to take this polynomial and look at the points where capital P, this capital P of 0, z, w is equal to 0. So I set t equal to 0. What's that going to be then? That's the equation that z to the 5 minus z cubed w squared equals 0. And I consider all the points in projective space of this form that satisfy this equation. And there's going to be 2 such points, right? Because I can scale this guy to be 1, and then so I put c equal to 1, then I'm going to get the equation that 1 minus w squared equals 0. In other words, w is plus minus 1. Okay, and if this guy is 0, which is also a possibility, then I couldn't solve this equation, could I? Let's check. So if I were to put z equal to 0, then what would w have to be? It would just, now I've confused myself. So w has to be non-zero, so I can make it equal to 1. And then it's just the statement that 0 equals 0, which is true. So that means this is also a point. So there's actually 3 points at infinity. Okay. these 2 points here, where this is plus minus 1, and then this point here. So in this case, for this particular affine algebraic curve, I needed to add 3 points at infinity to compactify it. Okay, last example of a complex manifold. You've learned quite a lot now, and some beautiful examples, but also quotient spaces. So if you have a complex manifold and you've got a group which is acting on the manifold properly discontinuously, what does that mean? It means that every point in M has a neighborhood such that if I take any group element G and I hit the neighborhood U with G, so I translate U by G, and I intersect that with my original neighborhood U, if that's empty, then that can only happen if the group element that I was translating with was the identity. Clearly, if you're hitting U with the identity, then you're not going to move U at all. But what we demand now is that if you don't hit it with the identity, then you move completely away. So you have no intersection with the open set you used to have. So you must be able to find such an open set. All right. So it's a very bad terminology. It's not, nothing is discontinuous here. It's really, we should talk about it separating group elements or something like this, but it's got nothing to do, nothing is discontinuous. Anyhow, then the quotient space of M divided by G, that is going to be a Riemann surface, and the charts are just going to be obtained by inheriting the charts from M. You see, the point is that the chart on the quotient space we can just take to be this U, because you know, in the quotient I'm never going to have a problem because I'm going to be identifying a point here with a point here, but there isn't any overlap with those points, so I can parameterize all the points in the orbit just by using this open set U. Okay, so for example, suppose you have a lattice inside the complex numbers. What is a lattice? It's a discrete subgroup of the complex numbers, thought of as an abelian group. Okay, then the quotient space is going to be a Riemann surface. So here's the complex numbers, and here's a lattice inside the complex numbers, all these dots, right? That's a discrete subgroup. Here's the 0 element there. So for example, this plus this is going to give you that, and so on. Now I can take the quotient of C by the lattice, and that's going to be a Riemann surface. And the charts are just going to be the same charts as the charts on the complex numbers, but you just got to take them small enough so you don't run into, you know, trouble where they overlap when you translate by pointing the lattice. So I can think of it as this region here where I identify opposite edges. Okay, and that's going to be a Riemann surface, and they're not all going to be holomorphically diffeomorphic to each other, right? It's actually the shape of this lattice is going to matter. This is called an elliptic curve. Okay, so I've given you a bunch of examples of complex manifolds, most of them one-dimensional, i.e. Riemann surfaces, but I also gave you some high-dimensional ones like CPN or like projective algebraic varieties. And those are some really good examples to keep in mind. Let's go to the next section.